Okay, so again, we have Professor Ludovic Marquis from University of Rennes, and he will speak on convex cocompact diffraction group from the last week. Okay, continuing from the last week.
Okay, so I we start from Monday. Okay, so we are talking about convex compact reflection group, and I still want to say two small things on Weinberg theory, two simple things. So it's point. Let's do black. Two simple points. So I want to speak about invariant subspace so that we have all in mind this. So a very nice feature of a group generated by reflection is that it's very easy to give the list of all the invariant subspace that you can have. So let me state the theorem. So you take W, an irreducible Coxeter group, and you take rho, a representation of W into GLV, which is a representation as a reflection group. In fact, you can put less hypothesis for the same statement, but let's keep things simple. Okay, so I have a reflection group, and now I want to say that I want to give you the list of all the subspace that are invariant. So subspace E, subspace E of V is rho invariant if and only if. So there is two situations, and that's a good moment to introduce two space. Important for the next. So the first case is when E is included in V alpha. So what is V alpha? V alpha is the intersection of all the possible kernel of my linear form. Remember, I have a group generated by reflection, so sigma I of x is equal to x minus alpha I of x vi. Okay? So I take the intersection of all the kernel of the alpha I, that gives me some space B alpha. Or the other possibility is E is contained in VV, and VV is the vector space span. So I don't know which you prefer, the span, the vector space, given by all the Vj for j in, so each time it's inside S. So the vector space span by all the vector given by my linear reflection. Okay, and the proof is nice. It's not complicated. So there is this implication is trivial. I mean, you just look, and it's clear. So I write a bit, but so if you take an x in V alpha and you take an S in S, then sigma S of x is x minus alpha S of x Vs, but this is equal to 0. So this is x. So any space included in V alpha, the action of rho on E is trivial. So in particular, it's preserved. It's even more than preserved, the action is trivial. Okay? And basically the same formula tell you that if E contain VV, then for any x in E, sigma S of X. Since you have this element which is already in E, this is again in E. Okay, so it's elementary. And so the more interesting stuff is the converse. So take E, which is rho invariant. So if E is included in V alpha, then it's done. So assume that E is not included in V alpha. So it means that you can find an X in E, you can find an S in big S, such that alpha S of X is not equal to 0. Okay? And then you should always use only the simple formula, so the definition of sigma S. So this is in E, this is in E, and this is not 0. So the first thing that you get is that Vs is in E, necessarily. So first point. Second point, you take a T in S such that MST is not equal to 2. Okay, so that means that alpha T of Vs is not 0. Okay, and then you look at sigma T of Vs. And by definition, this is Vs minus alpha T of Vs Vt. So this is in E. E is rho invariant, so this is in E, this is in E, this is not 0, so you get that Vt is in E. Okay? So I have one S such that Vs is in E, here. And so this gives me all the neighbors in my Coxeter diagram. Vt are also in E, but my graph is connected since my group is irreducible. So the connexity of GW, the Coxeter diagram, imply that VV is included in E. Okay. You stop me if there is any question.
So can I ask a question? So
Yes.
Okay, so in the Boxster diagram, there might be two vertices that might not be joined by an edge, but that means that the MST is 2, isn't it?
Yeah, so okay. So it means that, for example, the first one I have, let's say my Coxeter diagram looks like this. So I can imagine that at the first step here, what I get is that V1 is in E. Okay, so here I got V1 in E. And then as you say, M13 and M14 are equal to 2. But what I get is that V2 is in E because on my picture, M12 is equal to 3. Okay? And then I use the same stuff, but with this edge. So this edge gives me that V3 is in E, and then I can use this one or this one, never mind, to get V4 in E.
Oh, I see.
So it's the connexity of GW that give you vertices by vertices that will give you all the VT in E. Okay?
I see. Thank you.
Good. Thank you. Don't hesitate to interrupt me. Okay, so we have this invariant subspace. We have this list. So you can, if W is not irreducible, then there is a similar statement. It's a bit more complicated, but there is a similar statement. You can have a list, even in the non-irreducible case, but it's more complicated to state. Okay. Okay, once we have this, we can easily say when omega vin is properly convex. So the proposition is the following. So I don't recall all the hypotheses, but so A is of negative type. So I have a reflection group, a representation. I assume that A is of negative type and that the vector space, V alpha, that I gave just before, is reduced to 0. So it's what Weinberg called a reduced reflection group. In his paper. And in that case, omega vin is properly convex. Okay, what is the proof? So the proof, you go to the, so we are in the projective space, so you go to the vector space. So you consider omega tilde vin, which is a cone above, so there is two cones above, you choose one, a cone above cone of V above omega V. Okay? And you take the closure of this cone. So this is a closed cone, and you take the intersection with the opposite. And so this gives you something that you call I vin. And so you have a closed cone and you intersect it with this opposite. So what you get is, since it's a cone, you get that this is a vector space. Okay, and it's a row invariant vector space. Okay. And so what you say after that is that, so when you have so there is two possibility. There is one possibility you could have if you are at the level of cone. So if I vin is equal to the whole vector space, then it's an exercise to show that this means that omega tilde vin is in fact equal to the whole space. So the cone is everything, but we have already said that in that case, it means that W is spherical. So it means that A is of positive type, so this is absurd for us. So we are not in that case. So it's absurd. And so it means that I vin is not the whole vector space. Okay? And since I vin is not the whole vector space, it means that I vin is in the boundary of the cone. Okay. And now I use my previous proposition, and proposition tell me that Ivin is rho invariant. So either Ivin is included in V alpha or VV is included in Ivin. Okay. But this space is equal to 0. Okay, very good. And so this possibility, so this exactly implies, so maybe you should, if this intersection is reduced to 0, it exactly means that omega Vin is properly convex. Okay, so I need to rule out this case to show that VV included in Evin is absurd, and this is where I use the fact that that A is of negative type. So if Evin is of negative type, VV, sorry, is included in Evin, but we have seen last time we finished, I think, with that, is that using Perron-Frobenius theorem, we were able to show that to find an X that I call X good, that was the sum of, so it was the Perron-Frobenius eigenvalue of A times Vs, sum over all S. We have shown that this element was inside the interior of delta. So interior of the fundamental domain. But this element is inside VV. So it means that the interior, delta tilde, the interior of the fundamental domain intersect I E Vin. But E Vin, we say it's included in the boundary of omega tilde Winberg. And this is absurd because this interior has to be inside omega Vin. Not in the boundary. Okay. So the only possible case is this one, which means that omega is properly convex. Omega Vin is properly convex. Okay. Okay, so I finished with Winberg theory. So until now, everything I say was inside the Winberg paper. Now I go to the convex cocompactness. So first I will give the statement and make some remark, and then we'll go to the proof. So it's a theorem of, so I will call them D, G, K, L, M. So it's 10, I just did one time, so it's 10 for Jeff Denziger, François Guérito, Fanny Cassel, Gessan Lee, and myself. Okay, so I don't give the finest version, I give the main interesting core, and it slightly simplifies the statement. So I take a representation of a Coxeter group as a reflection group. So I assume that W is irreducible. So we have a version with W reducible, but it's I don't want to go in this fineness. I assume A is of negative type. And I assume that V alpha is equal to 0. So as we just saw, these two things give me that Omvin is properly convex. And so the following three statements, these three assertions are equivalent. You stop me if you have any question. So the first statement is the action of rho W on omega vin is convex cocompact. The action of rho W on omvin is naively convex cocompact. So I recall what it means. So it means that you can find C closed, convex, rho invariant, not empty, such that C mod gamma is compact. And without the naively, it's a bit more involved. So you need to take C very big. Big means that it contains that it contains the convex hull of the full orbital limit set, where the full orbital limit set is the union of all the accumulation points you can find on the boundary. And also, it's equivalent to a statement with two conditions. So it's the main thing that we want. So it's equivalent to the statement. So I write like this: no ZT. So this symbol stands for no. Okay. No condition ZT. So it means that there is no T included in S such that AT is such that AT is of 0 type and no IC. So this one means that there is no pair of I and J included in S such that Wi and Wj are infinite Coxeter group, and they are orthogonal. So I is orthogonal to J, and I orthogonal to J means that so this means that for all I in I, all J in J, Mij is equal to 2. Okay. Okay, so that's the statement. I hope it's okay. And okay, so I will try to explain NC equivalent to no ZT, no IC. I leave the no IC and equivalent to CC to the brave reader. Okay. So remark. So ZT is abbreviation for zero type. So no ZT means no zero type inside your Cartan matrix. IC is the abbreviation for infinite commutes. Because in this situation, if you have this, it exactly means that Wi and Wj are infinite and they commute. This condition means that they commute. Okay, so it's no infinite, no two infinite subgroup that commute, standard subgroup that commute. Okay. Remark. The second condition, no IC, only depend on W, does not depend on A. Okay. Another remark, this group, a group that satisfies no IC is a special kind of Coxeter group. So it's a theorem of Capras, or it's a consequence of a theorem of Capras. Capras' theorem is more general than that. If your Coxeter group satisfies IC, then it's a special kind of Coxeter group. So it has some Gromov hyperbolicity. It's not Gromov hyperbolic, but it's relatively Gromov hyperbolic. Relatively to what? Because this is important in relatively hyperbolic group to be relatively to what? So it's relatively to its affine subgroups, which are necessarily irreducible, and since it has no IC, of rank bigger than 3. Okay, so it's a very special kind of Coxeter group that are that can satisfy this hypothesis. Okay. And okay, I continue the remark. Another remark. Suppose that A, so I go for ZT. Suppose that A satisfy no ZT. Then it means that for every T included in S, if WT is affine irreducible, then WT is a special kind of affine Coxeter group, is of type A tilde. As we saw last time, Coxeter group of type A tilde are very, very, very special. Okay. And so I will call this property A tilde. So W satisfy. That's my definition of W satisfied property A tilde. Okay. And this came from this remark, the proof of the remark is that I will say it because we already say it last time. It came from the fact that if WT is affine, irreducible, and not of type A tilde, then AT must be of zero type. So it's a condition of compatibility with type. And so it came from the fact that A tilde is the only affine Coxeter diagram which is not a tree. Okay. A tilde, the family of A tilde N, are the only Coxeter affine diagram whose underlying graph is not a tree. Okay. So that's the only one that we can deform. Okay, so there is another proposition. I won't give the proof of this one. I just state it. It's not complicated. It's so it's from DGKLM also. If it's an existence of convex cocompact representation, so if W satisfy no AC and condition A tilde, so the only affine irreducible diagram are the A tilde, then there exists a Cartan matrix compatible with W which satisfied nosity. It's not completely obvious because you could imagine that with strange diagram, you could force at least one of the sub A tilde Coxeter group to always be of zero type, but in fact you can't. Okay. So you can always find a Cartan matrix which will have no zero type, and as a consequence, you get that you have a representation of rho, representation rho of W, such that this representation so always has a reflection group, and which is such that the action of rho W on bin is convex cocompact. And I did not state it here, but it's a trivial remark that if you have such a Coxeter group, then it satisfies no AC and A tilde. So no AC and A tilde is an if and only if condition for a Coxeter group to have a convex or compact reflection group representation. Okay.
Related to A or I mean the A that you got or any A or what is this? If this row corresponds to this A or any A. I mean this A.
Sorry?
Is this related to this A or any A? I mean the you say there exists A which is atomic.
If there exists an A, no, it doesn't mean that for every A.
It's just,
If there exists an A such that you have a convex to compact representation, then it means that your group satisfies no AC and A tilde. And if the Coxeter group satisfies no AC and A tilde, then there exists an A. But you can some Coxeter group have convex or compact representation and some representations that are not convex or compact. So I think it's my that's my last remark. So there is a family of Coxeter group that is very nice, which is Gromov hyperbolic Coxeter group. So I take W, which is Gromov hyperbolic. So in the case of Coxeter group, I can give you the, thanks to a theorem of Mousong, I can give you a characterization. So it means that W satisfies no AC, and the stronger condition than A tilde is satisfied that there is that only. So let me write. Satisfies that if T included in S is such that WT is irreducible affine, then WT is A1 tilde. Okay, so really this group. So the only affine Coxeter group that I can find in my standard subgroup is the trivial one with two generators. So basically it means no affine. But okay, so I need to allow the affine A1 tilde. And I take W, representation of W as a reflection group. So I just write like this. Then you have a very simple characterization. So rho W action on Ohmvin is convex cocompact. If and only if, you just need to check for every A1 tilde, in fact. So for every pair, such that MST. So I put big M. Let me stay with big M. MST is equal to infinity. We must have AST, ATS bigger than 4. Okay? So it means that the product of these two reflections is some proximal element. It's not a unipotent element. Okay, and the thing is that it's the only thing that you need to check. Okay, you just need to check that some standard elements are proximal. You don't need to check more than this. And in that case, rho W to GLV is Anosov. Now, more precisely, it's projective Anosov. So I won't say more on Anosov representation. I guess it was more the lecture of François that were on this subject. Okay. So we have a nice characterization of representation that are convex or compact, that are Anosov for Gromov hyperbolic group. And so, in fact, in that case, so I did not state it like this, but maybe I should have. Okay, so maybe I should state like this. Okay, sorry. So, in fact, the last statement is equivalent to the. Okay, maybe it's better like this. So it's an equivalence between being convex or compact, being projective Anosov, or having a few elements, a few carefully chosen elements, which are proximal. Of course, under the assumption, the very strong assumption, that your group is Gromov hyperbolic. Okay? Are there any questions? Okay, so maybe I can start the proof. So I want to start the proof, sorry. So the proof by an experiment. Okay, so I want to do two experiments. So two in dimension 2. So I take, so this is the hyperbolic space. And I take one hyperideal triangle. So my three vertices are outside the hyperbolic space. So I should have written here. This is H2. But if you want, it can be a strictly a convex, strictly convex. So which is in RP2. So I have free reflection across each side of my triangle. And we all know that this representation is convex or compact, okay? But I want to see why, okay? So what you want to do first is to, so there is a common perpendicular. So if I take sigma 1 and sigma 2, so if I take this side and this side, there is a common perpendicular to this two line, which is somewhere. So how do you draw it? You take this point, and then there is 2 points of tangency to the conic. And the line between these 2 points of tangency is the perpendicular. So here it's a right angle, here it's a right angle. Okay, now I should have drawn this thing in other color than blue. Let me do on green. Okay, and I do the same for this point, and I do the same for these 2 points. Okay, so I have tangency here. So my picture is more or less accurate, but okay, I stopped drawing. Okay. Now, remember what I say at the beginning of the day is that invariant subspace are easily classified. invariant subspace. So let me look at invariant subspace by the subgroup sigma 1, sigma 2. Okay, so the intersection of so the V alpha, so there is two special space, there is V alpha 1, 2, which is the intersection of the two kernels, so it's this point. Okay, and there is also VV 1, 2. I'm more interested in this one, which is the vector space or the projective space spanned by V1, V2. So I'm looking for, so technically this is P of VV alpha 2. So I'm looking, so this space, so it's generated by 2 points, where in RP2, so it's a line, so it must be this line. So this line here is the line V1, V2. Same, this line is the line V2, V3. Same, this line here is the line V3, V1. So this point must be V1. I put bracket because it's a projectivization of V1. This point must be V3. And this point must be V2. Okay. And now there is my knowledge of this action tell me that the good space that one should look at, if you have made picture, you should be convinced by that, is that this subspace that I will, so in red, this is what I want to call delta, fundamental domain. For W acting on ohm, so it's, yeah, let's just not the action fundamental domain on ohm bin, because delta can be a bit more than ohm bin. It's a fundamental domain. And in green, I badly choose my color. So let's say in orange, I want to put all this. So orange is D. So this is D. So it's the convex hole. I put a bar because I want to stress that it's closed for me, the convex hole. The convex hole of V1, V2, V3. Okay. And in green, it's delta intersected with D. And it's a fact that if you look at the action of rho W on the convex hole of the limit set, lambda of rho W, then delta intersect with D is a fundamental domain for this action. So under this experiment here, delta intersect with D is a compact subset of H2. So the action is convex compact. Of course, same in the bigger convex set omega bin. Okay, so that's the first experiment. I took the simplest example and I found a fundamental domain. Okay. Now I want to take the simplest counter example. So I take again H2. This time I take it's a semi-hyper-ideal. I don't remember how we're supposed to call these guys. So there is one point which is ideal and 2 points that are hyper-ideal. So again, I have pre-reflection. Again, so I put them in green. So there is a unique perpendicular to these 2 points, these 2 lines, sorry, it's badly drawn. And this point, this point is on the boundary, so there is a unique tangent. Okay, and for the same reason, we know that, okay, let me put my picture correctly. So this point is V1. This point is V3. And this point is V2. So if I take again D to be the convex hole of V1, V2, V3, always delta is my fundamental domain, my first fundamental domain, my main fundamental domain. And I take delta intersected with D. So this time delta intersected with D is this thing. So in particular, it intersects, in that case here, delta intersected with D intersects the boundary of omega B in that point. Okay. Sorry, I did not finish my sentence. So we see on that example that this action here, the action of rho W on OMVIN or H2, no matter in that case, is not convex cocompact. The thing maybe I should have stated, the important fact is that delta intersected with D intersected with OMVIN is the fundamental domain for the action of rho W on the convex hole of lambda rho W. Okay, so lambda rho W is the smallest invariant, rho invariant, non-empty, closed, convex subset of OMBIN. Okay. So on the smallest, my action is the fundamental domain is not compact, so my action is not convex cocompact. Okay. The strategy will be the same for the in general. Okay. Any question for the experiment?